Okay, you guys, so what we're going to do is we're going to now talk about section 10.1, the second half. Now we're going to move in. We already did the sampling distributions and we did the confidence intervals. So today I want to dive into talking about the whole hypothesis test, all right? It's going to be the same idea, right? Just like we talked about, your hypotheses are going to be P1 equals P2 or P1 minus P2 equals 0. For your null hypothesis, you're still going to have to go through phantoms, and I'll show you that in a second. One big change that I need to talk to you guys about, and this is, I started writing and I didn't have enough space. So here's the formula for your test statistic. All right, you're going to have two sample proportions. So your first sample proportion is going to be here, and your second is going to be there. But then we have a P, and it's not a mistake, all right, where I didn't put a hat on it. If you're going to have the P's here, okay, that's when you're going to have a pooled proportion. So if you have P hat 1 is this fraction, and P hat 2 is this fraction, well, we're going to add the numerators of the fractions, and we're going to add the denominators of the fractions. Your book models this notation, but your formula card models this notation. So notice this is a square root times a square root. They just multiplied the two square roots like into each other. So it'll be P hat, the pooled proportion, times the Q hat of the pooled proportion. Now, the formula card, and I just want to show you where this is located so you're on the back. Sorry, there's like a glare here. Hope this doesn't have a glare for you. So what I'm talking about is right here. Okay, for the confidence interval, it was this guy. All right, notice it's for two populations. So for the confidence interval, it was this guy. But if you're doing the hypothesis test, it's this guy, where if you see this sub C, this is your pooled proportion. I have no idea why they picked a C. No clue whatsoever. In other places, there's a bar over it, which I prefer. Just so it's less confusing, but I can't change the formula card. So you can write yours out either way. It doesn't matter if you write it as two square roots or one big square root with P hat, the pooled proportion, and then this is the Q for the pooled proportion, and then parentheses 1 over N1 plus 1 over N2. And I'll model this for sure as you go through. Okay, ignore this for a sec. I gave you your conditions. It's random, okay, two different random samples or two groups from a randomized experiment. If you're sampling without replacement, you need to do population at least 10 times your sample size for both samples. And then your large counts, just like with the intervals, you need to do N1 P hat 1, N1 Q hat 1, N2 P hat 2, N2 Q hat 2 are all at least 10. So if we take a look at example 3, high levels of cholesterol in the blood are associated with higher risk of heart attacks. Will using a drug to lower blood cholesterol reduce heart attacks? The Helsinki Heart Study recruited middle-aged men with high cholesterol but no history of other serious medical problems to investigate this question. The volunteer subjects were assigned at random to one of two treatments. 2,051 men took the drug gemfibrozil to reduce their cholesterol levels, and a control group of 2,030 men took a placebo. During the next 5 years, they studied the men, and 56 men in the gemfibrozil group and 84 men in the placebo group had heart attacks. Is the apparent benefit of gemfibrozil statistically significant? So, I just jotted down as I was working my samples here, okay, so I just could organize my thoughts. So, just like confidence intervals, right, we'll begin with our parameters. So we're going to let P1 equal the actual heart attack rate for men who take gemfibrozil. Be careful, it's not who took. It's we're trying to say, okay, from the people who took, can we generalize to all that will take? Right? There's 2,051 men who took it, but now we want to generalize that to the entire population of people who will take it. So we're using take. All right, and then P2 is going to be the actual heart attack rate for men who take the placebo. Okay, I set up my hypotheses. In order for this to be beneficial, right, if the medicine is good, then that means that this proportion of heart attack rates is going to be smaller than the placebo group. So if the rate is smaller, it's going to be a less than. So some people find it helpful to write the word above, right, like write placebo, write medicine, you ran out of space, but like write the words above just so they can organize their thoughts. Again, it doesn't matter if you use this notation or this notation, both are acceptable. You don't need to write both, just pick one and go with it. All right, but you can't like mix and match. You can't do this and this. You gotta go this way or this way. Assumptions, we need to check random. Be careful. These are people who volunteered for an experiment. So it's not a simple random sample, okay? It's not a random sample. They were volunteers. The key is here. They were assigned at random to the two treatments, okay? So that's the key. The participants were randomly assigned to the treatment and control groups. I'm going to check all 4 of my large counts, right? This is for, again, for Brozel. This is for the placebo. 1, 2, 3, 4. They're all greater than 10. I showed my work, as frustrating as that can be. 10% condition. This is different because we haven't had an experiment in a long time. You don't need to check. There's no sample being collected. If there's an experiment, we're not going to use 10%. It's not like a sample from a population. All right, so this is actually a condition you don't need to check when you have an experiment without sampling. If you're collecting samples, then yes, but these are volunteer participants, so it's not a sample this time, okay? Our name is a 2-sample Z-test for the difference in proportions. Okay, that's a Z. I should have told you before, you have the whole back page blank because this is a lot of work to show. So, for the test statistic, I wrote down my p-hat 1 is 56 out of 2051. I divided down and got this. My p-hat 2 is 84 out of 2030, and I got this. Now, if you think about percentages, right, let's just pause for a sec. And think, don't pause the video, don't pause the problem. Like, we're trying to see, is this rate lower than this rate? And so in percentages, sometimes it doesn't, right? You're like, 2.7%, 4.1%. It's lower, but it's not that much lower, right? But if you're talking about rates of people who have heart attacks, 1.4% is a big deal, right? That's big, that's huge, that's important to know. So we're trying to test, is this percentage lower than this percentage by a large enough margin that we can call it statistically significant, that we can call it, yes, that's a fact. Here is my pooled proportion. I took my 2 numerators and my 2 denominators, and then I came up with, this is a 4, can't read my own writing, and I divided this down, and here's my pooled proportion. Okay, so when I plug it in the formula, it's p-hat 1 minus p-hat 2, and then I chose to set up this one with the 2 square roots. So I'm going to have my square root here of, this is pooled proportion from here, and then 1 minus 0.0343 is the 0.9657. And I ended that, and I started a new one, and I did 1 over 2051 plus 1 over 2030. All right, let me model that on my calculator. If I do a big square root, right, and I'm going to have up top 0.0273 minus 0.0414. In the bottom, start a square root, 0.0343 times 0.9657. Go to the right, so I'm out of that square root, and I hit times, and then I'm going to start a second square root. So do you see how there's 2 square roots in the denominator now? I'm going to have 1 over 2051 plus 1 over 2030. Oops, I hit minus, hang on, over 2030. And I hit a minus back here. Yikes, glad I caught that before I hit enter. All right, boom. You'll see when you press enter, it like should look exactly like that. And here's my test statistic. Okay, like, I mean, this looks like this. Right, that's a good way to checks and balances. Did you type it in properly? So here's my negative 2.47. That's my test statistic. If we go back to our hypothesis, it was less than, which means left tail, right? So if you've got a left-tailed test, you're going to use norm CDF of negative infinity to negative 2.47. When you throw that in your calculator, you're going to get a p-value of 0.0068. All right, which means when you compare your p-value to alpha, your p-value is going to be less than alpha, which means you reject the null hypothesis. Your last test, your chapter 9 test, some people are just writing reject. That is not proper, and you don't get credit for that. It's reject what? It's reject the null hypothesis. You could write out NULL space hypothesis, or you can use H sub 0, but you can't just drop it. All right, so be careful with that. And what does that mean? If you're rejecting your null, then yes, that means that the P1 was smaller than the P2. The rate of heart attacks for the men taking the gemfibrozil was less than the rate of heart attacks of men taking the placebo. So you could state that, what I just said out loud, okay? You rewind if you need to rewind. You could also just say we have enough evidence to conclude that the apparent benefit is statistically significant, that the heart attack rate was lower for gemfibrozil than it was for the placebo. Okay, so there is a second problem about healthcare costs. If you would like, you could just pause and use pencil and try to set this up on your own. It's a quality thing to do. It's an important skill to figure out, can you solve these on your own or get going on your own? Okay, I'll walk you through though, for sure. So in an effort to reduce healthcare costs, GM sponsored a study to help employees stop smoking. In the study, half of the subjects were randomly assigned to receive up to $750 for quitting smoking for a year, while the other half were simply encouraged to use traditional methods to stop smoking. None of the 878 volunteers knew there was a financial incentive when they signed up. So at the end of the year, 15% of those in the financial rewards group had quit smoking, while only 5% in your traditional group had quit smoking. Do the results of the study give convincing evidence that a financial incentive helps people quit smoking? So we're going to let P1 equal the true quitting rate for employees like those getting paid, and P2 be the true quitting rate for traditional methods, okay, for people who use traditional methods. Null hypothesis, I'm going to have P1 is equal to P2, P1 greater than P2. We want this group to have a higher rate of quitting than that group. That's what we're trying to evaluate. All right. We've got assumptions. Subjects were randomly assigned to a treatment or control, or to the treatment groups you could write, something like that. Large counts, check 1, 2, 3, 4, right? Treatment group, control group, both of them. 10%, same idea as last problem, okay? And we'll have plenty of practice of non-experiments where you would just need to do, just like with the confidence interval before with the elementary schools, right? And their eating breakfast problem, you had to do both populations or at least 10 times your sample size. We'll have those too, but if it's the experiment, you don't need to check since the subjects in the experiment were not sampled without replacement from a larger population, okay? The name is a 2-sample z-test for a difference in proportions. Now we need to get into the math. So if we had 5% and 15%, and we had the sample sizes, right? If you have 878 total, I cut that in half and I got 439 for both N1 and N2. But we need the numerators to do this, right? So we have the percentages, but we don't have the numerators. So 15% of the 439 meant that 66 people quit using the money way. And 5% of the 439 meant 22 people quit using the traditional method. So that's where the 66 and the 22 come from. And you have to show that, right? You could move this down here and show it with this, but you have to show it somewhere on your paper. You can't just have like 66 and 22 appear out of nowhere. I got what, 88 divided by 878, I get 0.1. I threw it in my formula. I used the 2 square roots. You could also use the 1 square root, that's fine as well. I have no idea why I put a parenthesis here. You're gonna get 4.94. All right, so that means that it's gonna be a right-tailed test. 0, 4.94. We're gonna use p-value is equal to norm CDF, not 4994. I'm a mess, I'm sorry. Infinity, 0 and 1. You get 3.9 times 10 to the negative 7. So essentially your p-value is 0, okay? So the p-value this tiny is absolutely going to be smaller than alpha, which means reject your null, which means we have convincing evidence that the financial incentives help employees like these quit smoking. You could say the percentage or the proportion of those with financial incentives is higher than the proportion of those without the financial incentives, or the traditional methods is higher. Okay, good job. Hope you took marvelous notes. Make sure you let me know what questions you have. Make sure you practice typing these equations in your calculator. Make sure you know, like, after the past few months, we hopefully definitely, or a few weeks, we definitely know how to do this, but if you don't, let me know, and we'll go over it. Good job.